Okay, welcome back. 6 o'clock Tuesday, week 2. Yeah, I hope you're all enjoying the course so far. Is everyone enjoying the course so far? You can say no, I won't be offended. I'll just try and it'll make me work harder. Cool. I'm going to break script a little bit with the flow of the lectures today. I'm going to talk a little bit about Git. So I'll talk about bubble sort at the start again. We'll go back to sorting, and then I'm going to break script a little bit and do a small intro to Git, and maybe we'll come back and do it again because I realize some of you this will be your first time using Git and might be a little bit traumatic. So if I introduce it earlier, hopefully it reduces the trauma. There's a couple of edge cases with Git. I think explaining what it's trying to do helps a lot with the mental model for how you drive this thing, and that can negate a lot of the problems. That's what I'm going to go for today. I hope everyone's happy with that. In terms of homework and partners, everyone's got a partner. Does anyone not have a partner? No? Good. You all got started on the homework yet? Has anyone not started on the homework yet? No, good. You're better than I was. I would have been rushing in the last week. This is good. Okay, fantastic. And I haven't got anything in the chat saying they can't hear me, so I'm going to go forwards. Okay, so we're on our algorithms, and then so the whole part of section 2, I just started talking about sorting. What we're going to do in this section is we talk a little bit about, we do an intro to sorting by giving you, again, I'm going to drill home this point, the bubble sort is not a good sorting algorithm. It's just a good educational introduction to sorting because it's easy to think about, hopefully. The real point is it makes you think about asymptotics, which is a big deal, like how these things scale as the problem gets large, you know. How would you sort 1 million things? How would you sort 1 billion things? Like, these are not, you know, they might seem abstract, but it's like, I guess in my job in remote sensing, I do lots of things with LiDAR. LiDAR is a range arrays finder, which is like, they have them on everything these days. I think the latest iPhones have a LiDAR, but that's a really low density LiDAR. If you're doing like from a plane, like I used to do in a previous life, we'd collect like 1 million points a second of LiDAR as we flew along, scanning all of Queensland, trying to make a 3D map of Queensland. That's what we were doing. You know, so this thing of like, you know, you're trying to find the closest point to another point. How would you do that? This sort, would you get something that can scale to, you know, 10 to the 13 points or something when you're getting really, really large? How do you actually do that? That's what we're trying to get you to think about. So like, you can do this naive stuff, gets a little bit complicated. The next bit's going to be data structures. Then we're going to go back to more efficient types of sorting, which you would probably actually use in real life. Takeaway from this one is you learn how the low level things work and then use the clever one someone else built for you. Don't always try and write it yourself. Like, that's fine. Like, copying is fine in the real world, as long as people let you. Which gets to the end of this course, the end of this section, I'm going to talk a bit about software licensing and tooling. That's why I'm going to jump to Git, because that's an important part of the tooling chain. But I'll talk a little bit about software licenses, because that's a trap for new players, I would say. When you come out, you just use all the things. Like when you're in uni, you can just grab all this code from the internet, run it to build your project. When you go out, if you're working for a company who's going to try and make money off that, you can get in a lot of trouble. Or you can get the company in a lot of trouble, not yourself. You're fine. So I'll talk a little bit about that. So, okay, everyone happy? I will continue. Okay, so bubble sort. Bubble sort, as I said, it's bad. As someone asked, why does it name bubble sort? It's like, it's got to actually, I looked up after I said, like, it is that you can imagine the big values floating up and the little values trickling down. There's other names for it that people have come up with over the years, but I think that's the kind of thing. I thought it might be instructive just to show, we'll manually do the iterations just to go through it with my old friend Excalibur. So we've got this array 5, 2, 4, 1, 3, 5, 2, 4, 3, 1. And we're going to iterate through this from left to right. Every time we find a pair that's out of order, we're going to swap them, iterating across. So when we looked at this big loop, oh, it's not that one. I'm going to struggle to click on the thing because Zoom is terrible. We've got this inner and outer loop. So we're just basically going through this inner loop for the first one, then we'll cycle back to. So the whole idea is like showing why do you have to actually do this outer loop where you cycle back to the start? And it's like, after you do one iteration through, are you going to actually sort everything? So this inner loop, J is going from 1 to n minus I. Oh. Let's think about this. So we want to go through, it's basically just swooping through, and if we find a pair out of order, we're going to solve it. That's all I want to say. So bubble sort by hand. Anyone want to guess? So we're at this one, 5 and 2. Are they out of order? If we're going to hit that predicate. So what will happen? 2, 5. 2, 5, 4, 3, 1. We're unchanged. This is our first iterate. So what's going to be on the next one as we swoop through again? So I probably should annotate what the iterator is doing. So we're going to go I equals 1. Oh. Hopefully you guys can understand what I mean if I just write a tuple. 1, 1 for ij. Okay, let's look at this loop again. Oh. Okay, so j equals I to n minus 1. So we're going to go over to the next one. So next one is j is going to go up to 2. I will be 1. Oh, n minus I. Ugh. So what's the first iterate? We're going to be I equals 1. And then j will equal 1. And then this will go up to n is the size of the array minus I. So that goes all the way up to the end. Okay, cool. So we're going to move across. 1, 2. So on this iterator, just make sure I do it. We're comparing j with j plus 1. So we're still on that outer loop, still on the same bit. So we're going to go j plus 1. Are these two out of order? What's going to happen? So hopefully, I'll try and do this a bit faster because it's more slow than I thought it was when I had it in my head. 2, 4, 5, 3, 1. We're going to move up to the next one. 2, 4. These two are going to be out of order. 5, 3, 1. And then we're going to go up to the next one. 2, 4, 3. These two are out of order. 1, 5. So one thing you notice on this first iteration through, that the big one goes all the way up to the end straight away. So the big ones bubble up really quickly, but you'll notice that the little ones take a long time to come back down. Oh. Did I make a typo in the last line? Sorry, yes, I did. I was rushing. Those two stay unchanged. Yep, so swap, 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 all the way up. Yep, and then you go, okay, cool. That's actually not sorted by the end of this first loop. So go back through again, cycle through again. And again, the big ones will float up, the little ones will come down. That's
essentially like every interaction we pick the biggest one in the list and like put it
not really. We're just swapping pairs. So
but like after one iteration, we put 5.
yeah, the biggest one will always be the biggest one, right? So it's going to win every comparison. So that one goes straight up to the top. Then these animations of bubble sort, like you can, this will be like, rather than me tediously going through by hand, I just thought it'd be cool to see. You can see this with, this is the sort of thing. If you can see, imagine this is like a permutation that you're solving for as you go through by iteration. This is the kind of effect. So the little ones take a long time to come back down to the bottom. But the big one, as you're saying, go straight up to the top. That's kind of where the name comes from. Make sense? It's cool to watch. Just, I'd say, like, you know, best thing to do is pull it apart, do some print debugging, watch it through, you know, watch as it goes through the iterations. You will understand the method. Hopefully that's like, you can convince yourself that that's going to actually sort the thing. That's actually going to solve your problem. It's cool. What we're actually going to be worried about is like, how long does it take to run and how much memory does it use? These are two super practical problems. Memory kind of gets ignored a lot, but practically, as I think I said last lecture, it's like common crash for me. Common problem is running out of memory. I do a lot of work with cloud computing. Anyone familiar with cloud computing? As a word, you probably are. As a concept, anyone know? Anyone not know that, what that is? I rent someone else's computer on the internet. So for like 20 cents an hour, I can pay Amazon for a reasonable computer. and then I can run my code on their computer. They tend to be terrible little resource constrained computers. So usually it'll be like 8 cores, 16 gig, much like my laptop. I'll probably be wanting to run 8 versions of a program at the same time because I'm trying to process lots of data all at once. So that means I get 2 gigabytes per core. So that's a hard limit. If I run out of that, I'm going to crash the instance, that thing will die, or that job will typically die, and then I have to recover that job. So like worrying about how much memory an algorithm's going to use and how long it's going to take are 2 things. I'm paying 20 cents an hour. That's like, that's an optimization. The other one's a constraint, if you want to think about it that way. Like I can't run out of memory. I can take forever, but it'll just cost lots of money for somebody else. I don't pay for it. I might have questions to answer at the end of the month though. Okay, so that's what we're trying to go. So there's better timing. So has anyone actually seen benchmark tools already? Is that everyone familiar with that? I would recommend using this, and we haven't used it in the notes. Especially when you're trying to work out, oh, I haven't added it. My computer's fresh. So this gives you very accurate timing. Julia, one of the problems is pre-compilation with the way it works. It's like, so the first time you run a program, first time you run a function, it'll be a little bit slow. Second time you're good. So there's usually this little bit of startup overhead. It's actually a lot better in 1.9.2 than previous versions of Julia. It's getting better because it's probably the main criticism or barrier to adoption for this language is that problem of startup overhead. So benchmark tools, what it will do is when you're timing a function, you get this little macro at b time. Again, you don't know what something is. So this uses a benchmark macro. So if you're going to try and time a function, you can use this at time. Macro comes built in with Julia, but benchmark tools is it will rerun it multiple times and gather statistics. So you get a better idea of what the actual runtime is. If you're just doing one time, it's pretty rough. And you'll see that in the notes where there's a bit of jitter on the timing because we haven't been super careful about how we're running the timing, doing the timing profiling. B time takes a little bit longer currently. So time is to time the execution of a function. So if you've got something super fast like print, it'll be so fast that you'll basically not see anything. That's really fast. You get this time, and it says about allocation. So that gives you a hint about memory, what it's doing in memory. If you do B time, you probably don't want a print statement in this thing because you'll notice that it's running lots and lots and lots of times to gather accurate statistics. That's a stupid one to give an example, but I'd recommend using benchmark tools for the stuff you're going to do in your homework if you're trying to work out why a program's running slow. And this other one, this is your friend when you're trying to go fast in Julia, at code warn type. So if you have a function and you're trying to hunt, the thing that makes Julia's code slow is type instability, where the compiler can't figure out the type at runtime and it has to promote to a super type. So that'll come up more later, but code warn type basically makes red. It'll give you a hint in where in your code it's going to be running slow. That's another one. Anyway, so
Could you give an example of how you use code?
I'll have to think about how to make one. I can do this one. I can make a function test func. If this doesn't work, I will come up with one for the next lecture and share it with you because there's a chance I'll get this wrong. Okay, so y equals 1 plus x, return y. And okay, so at code test func. Okay, if I run this with an integer, I'm going to add an integer and an integer. And should be all blue. It's fine. If I run this with a float, it's still fine. If I run it with, no, that's still fine. So I have to engineer all these primary types that kind of, let me think about what I do. Maybe if I do, no, that's still fine. I'll come up with a good example of how to add a trigger type instability. Basically, it's like I'm going to try and do an operation, and at runtime, it can't quite work out what X is going to be, and it will promote to type any, and it will be slow. But I'll come up with an example that'll actually work. Okay. So we had this naive implementation of bubble sort. I think I already talked about this one. So timing. Okay. Data is that. And basically, if you want to time at time, bubble sort, data. Okay. So, for this tiny array, again, startup overhead, if I run it twice, it's much faster on the second time. So hopefully you guys could see that. On this first time, it took 0.02. On the second time, it's super fast. I reset the data because remember this thing, it's going to mutate the data under my feet. So it's already sorted, probably going to be faster. Got to make sure, I'm actually timing the right thing. So that's super fast for a tiny array, but, 8 elements, is small. We're going to be interested in how does this thing grow as the data grows? And it depends. This is why these algorithms depend on the distribution of the data as well. So you can have this shortcut thing where you go hey, I didn't do any flips. It's already sorted, bail. So you're kind of interested, a good model for the data you're going to see when you go to run this thing for real is just random data. So we can use random. We're going to set seed of a random number generator. I think I showed this in the first lecture, but in case that's not clear, if I draw a random number, draw another random number, they're pretty much random. If I set the random seed back to 0 and I draw a random number again, it should be identical to this one here. So pseudo random number generator. If I set the state, you'll get the same thing. So the idea of doing this is so we get some reliability with our timing. We can draw 10 to the 4 random numbers. And if we go at time, sort data. So for 10,000, took a little bit longer. If I'm in the REPL, if you want to suppress the print so you can see a little bit better, you can put the semicolon on. Not necessary when you're writing functions in code, just when you're working in a REPL. I don't want to see what it's going on there. So for 10,000, it managed to do it in 0.14 of a second, which is pretty fast. I couldn't sort that in that fast. Computers are amazing. So this is a bad sorting algorithm. That's how fast it goes. Now, here's the depressing thing, though. We'll regenerate data. We'll reset this random seed, regenerate data, and we'll just compare the timing of bubble sort with the inbuilt Julia sort. Bang. Wow. So there's a hint that you could be doing better. I could have just implemented this very badly. So I see those timings in here, different on a different computer. So this was run on probably Yoni's computer when he compiled this document. It'll have executed all this code in Weave. So we see a similar thing where, it's quite a big difference. So 0.0, 3 zeros here, no zeros here. Heaps faster on 10 to the 4 data points. So something's going on. Not just software tricks, it's algorithmic tricks. Okay. Now, this is teaching you bad tricks that I probably shouldn't teach you, but I'll just talk about it anyway. So one of the things you can do, this is kind of a hack in Julia, so use with caution, is there's this macro called inbounds. And I kind of discourage the use of it unless you're really, really sure you know what you're doing and you're not going to go out of bounds of the array. What this does is it turns off bounds checking for an array. So if I'm iterating through, let's make data small, x equals 1, 2, 3. I'll put some commas in there. Okay, so if I go, in terms of bounds, this one, 1 is the start and 4 is the end. If I try and do 5, I get an error. What it won't do, Julia, if you turn off bounds checking, it will happily go beyond the array into some other random bit of memory and crash your computer, crash the Julia session. So don't do it, but if you're trying to go fast and you're guaranteed that you're not going to iterate outside the bounds of the array, you're kind of fine. So that's this dirty trick here, is this inbounds. So we can check, you know, we're going to do dirty software engineering hacks. That's what this is. Slightly faster bubble sort. So we go random seed, regenerate the same data at time, slightly faster bubble sort, data. So first time, not so fast. Random seed, I'll regenerate it. And it's like, it's tiny, tiny difference. Like it's in the noise. Like, so we did a dirty trick that might crash the program badly, like crash the Julia session badly. It's not that much better. So interesting. Oh, that's for smaller ones. But yeah, I'd say, like, I think this is probably actually going to go away in Julia. This inbounds macro is something that they'll probably fix, so you don't need it anymore, and it's just fast. But that's a trick you can do, and it's a catch for indexing into arrays. You need to be a little bit careful. Still miles off, like dirty software tricks are still miles off being clever. And that's the point for this course, is like, be clever. Being clever with the algorithms is the biggest win you can do. Like, it's not so much language to language, although, you know, you're in a fast language, it's good, speed's good. But it's this difference between the asymptotics. It's like there's a constant out the front of this thing. It's n squared times a constant. You're only making that little constant out the front smaller. You're not changing the scaling behavior. It's never going to solve it for 1,000,000. Like with the way this is going for 10 to the 4, if I try and do 10 to the 6 and it's quadratically scaling, it's going to take forever to run. Okay, here's a empirical investigation of timing. I won't actually run this one, but I'll just talk through what it's doing. So this one is initializing an array of times. So this is a bit nasty. So it's a vector, a float 64, undef of size 0. An easier way to do this is just to go float 64, blah. You can do that. So like if you want to make an empty array of a type, you put the type out the front and just put the square brackets. It's an easier way to do that. This is kind of the long-winded way of doing the same thing. Similarly, I could make, you know, int string, although it doesn't make sense in this case to do that. So we're going to do times, and we're going to go through 500 in steps of 500. So this is the way of defining a range. Remember I said, I've shown you iterators before where I've gone like 1 to 10. And I go like, what's this guy? It's type of blah. It's a unit range. If I want to turn that into a vector, can anyone remember what that was? Collect, good. Okay, cool. If we don't want to step by 1, we'll say we want to step by 2s. You just put a 2 in the middle. So 1, 2, 3. It won't actually respect the size of the last one you're doing. It will do it in steps up to the one you've given. So what we're doing here is we're going to generate random data of size n. That's what this for n in n range. It's going to start at 500, move up in steps of 500, up to 10 to the 4. We're going to start the time. We're going to run bubble sort. We'll collect the n time in nanoseconds. That's what that time ns function does. Give the time in nanoseconds. So if you run this guy, A equals blah, B equals blah. If you got A minus B, that will give you the time as an integer of nanoseconds between those two events where I ran that function. So that's a way you can do timing. Hope that's clear. So nanoseconds are really small, you know, so like the computer itself won't be that accurate at timing, but it's a thing you can do. Yeah, so what we're going to do, so that one turned into milliseconds. That's equivalent to what I just did then. If I do B was second, A was first. So it was like me, the time difference in milliseconds for me running A function and B function above was 2000. So 2 and a bit seconds between those two. That's what this bit of code does. And then it will push this thing to this array that we've initialized times. So hopefully I've shown this before, but if you're going to go x equals float 64, if I want to add a value to this array, this is useful when you don't know how big an array is going to be when you're starting a function. Like maybe question 6 is like this, where you don't know how many things you're going to collect. So you want to initialize, you can't really initialize it. So you just can push them on. It's slower than pre-allocating the array, but if you don't know how big it's going to be, it's a thing you can do and it's kind of safe. So if I go push onto x 1.0, then I push on 2.0, and then I push on 3.0. So that's what x ends up being. Cool. Hopefully that's clear what that code's done. It's pretty brain dead. It's just running bubble sort, pushes them onto an array, and we can make a plot. Here's some more of this plotting syntax. We can see, oh yeah, cool. We did this heuristic thing where we just went like, oh yeah, there's 2 for loops, should be n squared-ish. Does it look like it's scaling quadratically in practice? Because, you know, there's theory and then there's the practice of running this thing on the computer. We don't know what Julia is actually doing with our code underneath. Does it actually scale in the same way?
I brought this code into my computer. Sometimes right at the beginning, it has a bit of spike upwards and then goes down.
It would be this overhead of pre-compilation, most likely. But if you use B time, you won't see that. So as I said, this is just for the notes. Real life use B time because it's going to be careful, but it's much slower to run. So, you know, it's when you're being careful versus hacking around, which lectures are hacking around. You'll see that, like we had that for some of these other ones, like that. That's one of these ones where you get like a burp, little burp in the timing. Cool. Okay. So that's an empirical test. Cool. Who's a statistician here? Is anyone a statistician? No, not yet. How would we prove that this is like a deep question that seems stupid. How would we prove that this is quadratic? Yep, cool. So you could do a least squares solution. What have you got? Yeah, of testing. That's right. Like the very sort of, so this thing, I kind of want to say this. It's like, it sounds trite. You can fit a quadratic model to it and you go like, cool, that looks right. Because it's like, fits a quadratic really well. If I fit a cubic, it probably fits well too. If I fit a quartic, it probably fits well as well. And like, so I can keep increasing this model order and like, they all fit pretty well beyond a certain point. So there's this question of order selection is not trivial. So that's this next bit of code. We fit, this is if you want to see a bit more, some of these deeper packages. There's this GLM package with Julia, which is like general linear models. So you can set up, so the data, this is something that will come up, data frames. Has anyone has anyone not used pandas? I've got to think about it in the negative. Pandas? Not a thing. It's a way of organizing. It's a data model for tabular data that's really popular in Python. It's a data frame. So if you've got tabular data, let's give you an example. Sorry, can't type. We'll talk about this a bit later. I think Andy goes on about this for a while. Oh, wrong syntax. So you can make this little table with columns A and B, so you can give them a name. Yep. Better, yeah. So we can make a little table with column names and data in them. These will typically be an array though. So you'll have something like 1, 2, 3, 4. Now I got to write out lots of strings. A, B, C. So you got a table with a type. Each column has a name and a type. This is really useful. If I want to get out the A values or I want to get out the B values, I can get those. It's a common way to load data in for doing manipulation, doing statistical stuff, really useful, like a CSV, or an Excel sheet in lots of programming languages. We can set up a model as a linear model. This is we're trying to solve for a quadratic coefficients. the coefficients for a quadratic. So there'll be an a plus bx plus cx squared. This will fit a linear model to the data. I won't run this, but it'll give you an idea. And these are all those, as you said, they're statistical tests, but there's no order selection here. So model order selection. So you can do any hypothesis test you want. It's got a t-test to go like, what's that p-test? It's like, yeah, cool. It fits a linear model, fits a quadratic model really well. Cool. You can do that. Is it convincing? I wouldn't be convinced by that, but I'd be convinced by doing the analysis that comes later. I'd say there's like an engineering version of this. Like if I say that, it's not disparaging of engineers. A lot of my best friends are engineers. What's the engineering version of doing this analysis? I don't know if we did that in these notes. You plotted on the log plot, right? Like, so if the coefficient, you should be able to turn it into a linear thing by just taking the log. So if you plot the log of the runtime versus n, you should be able to see, what's the slope of that guy? Yeah, cool. So there's another bit where this would actually be more of a valid statistical test. This is like cross-validation. We're going to go, hey, let's generate a number well outside the range of what we ran. Can we predict what that runtime is going to be from the model we fit from this data? So we'll extrapolate well beyond where we fit the model. And does it do a good job of predicting? And it's like, yeah, kind of. You could make this more precise by calculating your projected variance outside the model range. You can do all those sorts of things. So it looks like it's pretty dirty, but it's like, yeah, it looks n squared, Yeah, this is the engineering version. Sorry, if you plot it on a log scale thing, they're dividing it by different coefficients. Does it look like a flat line? That's kind of the same thing. Okay. So order notation. So I've said this to you plenty of times, just want to introduce it a bit more formally here, or not formally. I'm going to be really informal and just say like, oh yeah, it's order n squared. That's the thing. I've said it's order n, order 1. Order 1 is the best thing you can do. Like, that's great if you can do that. I test people's intuition. What do you think the order of matrix multiplication is going to be? I have a matrix of size n by n and another matrix of size n by n. What's the order of matrix multiplication going to be? N squared would be just reading out the elements. N cubed is like, if you did it, the run and dive, right? Like, sure. If you do that, that's n cubed. It's actually n to the 2.4 currently. So it's in between those two. So there's a clever algorithm for doing matrix multiplication that's n to the 2.4-ish. Anyway, I'll leave that out there. So, and that's a big deal, like going from n cubed to n 2.4-ish and, oh yeah. Oh yeah, sorry, but your hand was up, yeah. If you think about the run and dive thing, you go like that, this times this times this, plus, plus, plus. Think about how you do matrix multiplication. That's n cubed. But so I think it's called Winograd's algorithm is the one people use. It's n to the 2.4-ish. It's not actually asymptotically the best one. So there's lots of clever computer scientists who figured out n to the 2.3-ish ones, but that coefficient out the front makes them impractical in practice. So we were talking about factorial. This one here, order 2 to the n, exponential growth. That's kind of like the worst case. So you can think about this of like, who likes set theory here? Who's a proper pure mathematician like set theory? Nobody likes set theory. What's the cardinality? If you've got a set of cardinality n, and you've got the power set of that set of all subsets, what's the cardinality of the power set? 2 to the n, right? So you can imagine there's a mathematical problem you want to solve where you have to enumerate every subset of that set and check them all one at a time. That's what 2 to the n means in practice. And we saw how quickly the n factorial grew. By 20, it's impractical. So there's famous problems that have this, 2 to the n runtime. Anyone know of any examples of this? Does anyone? like practical problems in industry that people have to solve every day. There are actually examples of this where it's like, the famous one I'd say is like traveling salesman problem. Is anyone familiar with that? So the setup is I've got cities somewhere in a, you know, you're going to have the positions of these cities and you're going to go, I need to visit each city once and come back to where I started. And I want the shortest distance possible between all those cities. That's one of these ones that scales like a factor, like scales to the power of n. The best known solutions still scale to the power of n. It's an open question about whether, you know, there's anything better than that. Pretty much no. But this is like if you're, you know, an airline trying to route planes, traveling salesman problem, multi-agent traveling salesman problem. If you do operations research, you come into these like every day, like lots and lots of practical problems are the best known solutions that are exact have this sort of scaling. So your job as a mathematician working in operations research is, can I do a tricky one that's faster than this? That's like good enough. So like, it doesn't matter if it's exact, but faster is better. Cool. That's the discussion. So like, we've got bubble sort here. Again, this is why is bubble sort O to the n squared? I think I led the lecture with this one last time of like, there's the two bits that are doing, we're iterating through this loop, then we're iterating through it again, you know, just to make sure we've gotten to the end. There's two parts to this. There's a comparison. We're going to access the element at j. We're going to access the element at j plus 1. We're going to test for greater than, less than, and then we're going to swap the positions. So this comparison and switch are the bits that take time. So they're the bit that you're going to add up to go like, this is the thing that drives this order of comparison. So you can go through, it's basically just counting from here. You just count up how many times. Outer loop runs n to the -1 time. Inner loop, there are blah, 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 just add them up. So if we add up all these guys, it's going to be n times n minus 1 on 2, which is half n squared minus n on 2. So in order notation, we just care about the biggest one, n squared. You can go through that yourself if you don't believe it. Basically, that's this, never hurts to check. If we just add a counter and we can validate that how many times, and again, we care about this comparison step and we care about this switch step. So we're just counting how many times we hit this bit. And we just want to show that it matches the equation. So you can do that. You can validate that for values of n. That's where we're going to. Okay, that's clear that it's n squared. Everyone believe me? Everyone, oh yeah? Yeah, yeah. That's a different way of thinking about it, yeah. Cool. Okay, I think this is good to talk about, and then I'll spend 10 minutes, 15 minutes talking about Git. You can take a function as an argument in Julia. So like, this can seem a little bit strange. We've talked about variables, but you can take a function as an argument, and that's super useful. So what we're going to hear is we're going to take an optional named argument called comparison where it's greater than. So what we're going to do, if you notice this bubble sort compared to the previous one, this bubble sort, we had this line here where we're going to go AJI is greater than that. If you look in the lecture notes, we've swapped that out for running as, you know, not in fixed notation, prefix notation for the function. We're going to run comparison A, B. This lets you change the way you're going to sort. So we can go function bubble sort. If I go data, rand, oh, I don't want that big. I just want 10. I just want 10 little ones. Just do that. Okay. So if I run bubble sort on data, okay, we're sorting from lowest to greatest. And because we have this optional named argument as a function, we can change that out for comp equals less than. Hopefully it'll sort it the other way. So this function, you can pass around a function as an argument, use it inside the function. Really useful thing to be able to do, makes your code much nicer if you can think about how to do it. You just have to think really hard about, what's a useful thing in here. So to being able, the ability to take any function is kind of weird. Yeah, like you can use one that might not make sense and see what happens. It's got to be a Boolean function. So a Boolean function that takes, anyway, we can think through that. That's just a bit of syntax that would be useful. I think in the homework, you're supposed to do that, like pass a function and mess around with it so you can do string stuff. Okay. That's fine. I'll come back to this. I think I'll stop here. Any questions on that bit? We'll just make sure we return to this on Monday next week. I'm going to go down and we are going to talk about, I'm skipping right to the end and I'm going to talk about Git. Anyone, again, raise your hand if you haven't used Git before. Okay, who has used Git? You've used it a little bit? Well, how do people find Git? Like people who've used it, what's your been experience with Git? Good.
Yeah, good.
Oh my God, yeah. Has anyone been traumatized by Git? In the last month, I've had at my work, it's taken over a week for people to resolve a Git merge conflict that was for too long running branch. So even for professional software engineers, this stuff can be problematic. If you're working on your own or in small teams, it's easy. The problems come when you're trying to negotiate on big projects. So I guess my first thing is like, desiderata, like what are we actually trying to do with version control? And like, I'm old enough to have, when Git wasn't the dominant version control, I think the first one I used was CVS. Like it was a very different philosophy, design philosophy to Git. Or subversion was, subversion. Yeah, so they've changed over time. And this will be familiar to every student when you're writing an essay, right? Like you're writing a Word document and you're going to go, maybe not so much these days because they have revision changes on the online version of Word, but old version of Word, you're going to go like, this is my assignment, version 1, and you do it in the file name. And then you go, oh no, it's not version 1, it's version 1.1 because I've changed the thing. And then you go, it's final, version 1.1 final. And then it's, no, that wasn't the final, it's version 1.1 final. And trying to do it in the file name, and then you realize that one was bad and you want to go back to the first one when you didn't say something stupid, blah, 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 blah. This is kind of a normal thing, and it's normal in software. So you want to keep, if we've got software, we want to keep track of software over time. So if you've got some code, has anyone had this with their homework where you've got a working version for one of the questions and then you break it and you can't get back to the non-broken one and it's a descent into hell? Yep, that's what version control is for. So that's why I wanted to bring it up a bit earlier than we usually do, because it's useful to use. And the earlier you use it, get the problems out the way, it's good. So being able to revert to a previous point in time, doing this thing, you can break something important. You should feel free to experiment with the code and not be scared you're going to break it and not be able to recover. That's the big thing. Like it's a huge thing. You want to keep version. In professional ones, sometimes you want to blame and who did what at what time to break something, because that's important too. And in Git, that command is actually called git blame. That's the thing. So be aware of that. I can show you how to fix that with git config though, so you can pretend you're someone else. No. Yeah, so you want to you want to experiment. Like you want to be able to be super flexible in changing stuff and keep a good version that's kind of unpolluted or be able to go back to it. That's the whole idea. This one's a kind of a practical one. It's like you want to keep a remote version on someone else's computer that's like rated and not going to, the cloud is just someone else's computer. Their server can catch on fire. It's like, does happen. Like, is everyone familiar with Amazon Web Services? It's probably not a thing that enters into your mind very much, but it's like, this is this thing of renting someone else's computer. They actually set up their data centers and they call it a blast radius away. Don't think about that too hard. So that if one goes away, there's a copy of it somewhere else that's nearby. So they've actually duplicated the code. That's how they can guarantee that if you've saved something in the cloud, it's in this place and in this place. So if that one goes away, you can come and get it back. These are the types of things they think about at scale. It's like, it's really, the horror stories when I was an undergrad of like someone losing a laptop with their thesis on it right before they were going to submit it. And it's like, you know, so having this like remote backup in case of a disaster is super important. And the last one is probably where Git fails, I would say, but you can work around it, is allow teams of people to work on a code base without treading on each other's toes. So like, has anyone got like a Google Docs and had 3 people try and write it at the same time? Have they had a good experience of doing that? Not really. Oh, you have? Yeah, the usual trick is you just keep apart, right? Like I do this bit, you do that bit, you do that bit, and keep it apart. That's kind of the same with Git. So Git was created by Linus Torvalds in about 2005. Linus is a famous guy in software because he was the father of Linux. I'm the first person who wrote Linux. He wrote this version control to deal with writing the Linux kernel. So that's a huge software project. It's very weird in its design. It is a distributed database is basically the idea. So you have this idea of a Git repo. Has everyone downloaded Git Bash yet? Have you cloned a repo yet? I'll show you that really quick. Okay, so Git, anyway, I put a bunch of links to a cheat sheet here. Oh, this Atlassian cheat sheet. So this is linked to in the lecture notes via Atlassian. They're an Australian company who did well. Git init creates an empty repo. So if I'm a lone wolf, so Control-Shift++, because that's too small, go to my computer. This is where I have a folder on my computer called source, where I've got something about 2504, Paul's silly test repo number 2, time series. I want to make a new repository. I'm going to make a new place to put my code. These are some Linux commands I haven't told you yet, but make is to make a new directory. And let's say I call it git test. Cool. So this first command is like, I want to initialize a repository, create an empty git repo at a specified directory. So if you don't give it arguments, git init, the thing is like you can say where to do it here. If you don't say anywhere, it'll make it where you are. So I want to go into cd git test, git init, blah. Okay, a little bit of spew about, this one might trip a few of you up. Older versions of Git called the main branch master. Newer ones call it main because it's probably a better name. Master has lots of connotations with bad histories of slavery and stuff, so people ask for it to be changed, which is good. I'm old and I'm fossilized, so I always tend to call it master because I'm so used to dealing with it. This is like nothing. There's nothing here. So what I'm going to do is if I show you some crusty Linux tools. Vim is a text editor. Test.text. I'm going to make a text file in Vim, and I'm going to write something in it. Because Vim's annoying, it's this modal editor. So I've just written a text file with hello in it. If I go git status, this is this next command. It tells you the status of your Git repository. So to go on branch master, nothing's committed. There's this file here that I'm not tracking. If you want to track it, basically tells you what to do. It says add this file. I go git add test.text. I'm going to go cool, git status. Okay, cool. On branch master, no commits yet. There's a change ready to be committed. So now Git is going to track this thing if I commit it. So if I go git commit. Okay, it pops up this weird little text editor. So if you're using it from the command line, you're going to get, so I'm just showing you this stuff so you see some Linux stuff. This is Nano, it's a different old text editor. And I'll say first commit. Control X. Yes. Okay. I've made my first commit. Git status. Okay. On branch master, nothing to commit. Git log lets you see the history of commits. There's only one here. First commit. I use a tool called git k that lets you see the whole history. It's a visual version of this. So basically, if I edit this file now, Git's going to keep track of that and let me know. If I go vim, what do I call it? Test.text. Hello, everyone. Escape, right, quit. Okay, git status. We'll say, hey, this thing's modified now. Test.text is modified. You might be interested in that. So git diff. This will show you what's been, this is really important. So this is central to the way Git works. What Git will do is it looks, there's a function, a Unix function called diff that everyone uses that goes line by line through a function and shows you what's changed. And so if a line's changed, it'll look at these differences and make and let you track that, okay, something's changed. So everyone's changed. So if you want to get status again, if I want to add this, test.text, cool, get status. This thing's modified. So again, I want to keep this. I'm sure that this is good. I'm going to commit it. So there's this two-step thing that can trip people up. You add it, and then you commit it. Make sure you do that. Second one, second. Or first edit, I should say. So there's first edit. Control X. Yes. Okay. Git K. If we look at this now, there's this tree of commits. So there's this first commit where I've added hello. And then there's a second commit where I've added hello, everyone. So you'll notice this thing here. There's this funny index that it's saying here, blah, 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 blah. It gets a funny database. So like what it does is it takes the diff and then hashes that diff. So it runs it through a mathematical function that will turn that diff into this random string that's unlikely to run into another string. The reason for this is so if you have that string that's hashed, the git hash, git char, some people will call it, because of the way the cryptographic algorithm works, you can recover back to that point in the tree. A little bit complicated, might seem a little bit low level here. Basically, every time I make a commit, I can go, I'll do this edit, commit, no, I'll do add, commit, and then it will keep track of all these ones. And if I want to go back to a different version, I can check out that hash, go back in time. You can also make branches. This is like your first introduction to Git. GitHub is another thing. I think, has everyone got a GitHub account? Yep, cool. GitHub, the whole of I want to say the design philosophy for Git is that it's decentralized. There is no one version of the repository that's the good version. Every Git repository is its own Git repository and they're all independent. This is kind of counter to this idea of having a remote backup. So everyone kind of wants this thing. It's like the whole internet was designed to be decentralized, but then everyone wants to go to one place to get the thing. So GitHub is this useful thing where it's like the remote version of your repo, and you want to keep syncing it up with that repo. And this is the bit where it gets unstuck. If I'm just working on my Git repository, it's fine. I can check, add out, make branches. I didn't talk about branches here, but look through the cheat sheet. That's basically if I want to, I've made all these commits and then I want to do an experimental branch. I can make a branch and go off sideways and do stuff. That's when it gets hard. Then you got to merge it back in. GitHub is for hosting a remote version of this that you'll periodically have to come back to and sync up with. So source notes, that's me. Don't use GitHub much anymore. You can see there's a couple of these repos here. So Has anyone created a repo yet on GitHub? Has anyone not? So it's pretty straightforward. Just click on repositories. So all this stuff I was doing at the command line is basically automated in GitHub. So GitHub's not Git, it's a separate thing. It's a product built on Git that lets you manage it in a remote thing. So this is hosted in the cloud somewhere. Create a new repository. Repository name. What do we want to call it? Test repo. Test repo is available. If it's public, this is open source stuff. Yeah, I think you can have as many as you want. It used to be, maybe I'll run out. I don't think how. Does anyone know what's the limit? 8. Yeah, so I think I should be good with this one. You can create a public repo. You can create a private one. If you want to create a private one, you're probably limited, especially on student accounts and stuff. There's a bunch of stuff to initialize, like an empty repo like I made is kind of useless. First thing you might want to add is a README. You might want to add a git ignore, which I would recommend. These are for different languages. So this is like super helpful. So you can go through here and go like, hey, I'm making a Julia repo. So there's going to be some stuff that I don't want to track in Git. So Git is only for text files. Because of the way this diffing works, if you keep data in Git and you diff it, you'll make your Git repo very, very large, very, very quickly. Because it will keep a copy of the data. So like if you had an image and you change 1 pixel in the image, the diff between those two things is basically the whole image again. Whereas with a text file, I'm just adding, oh, at line 203, I changed it from an X to a Q versus I changed a pixel. The way an image is encoded is not as a text file. You're going to get the whole thing copied again. So don't keep data in Git. Running out of time. So the last thing I'll say is like, don't keep passwords in Git. Like it seems dumb, but every place I've worked at has done it. Someone has done it because there will be robots that are just looking through GitHub for things that look like passwords. Fun, hey? Yeah, you can do that. It will create it. Choose a license. I recommend MIT or BSD. We'll talk about that later. Create a repository. Cool. Now, code. There's different ways to set up the security of these things. It used to just be you could use a username and password. They've taken that power away from people. The two options are via a token or via this thing called SSH. SSH is, here I launched a terminal. If I want to launch a terminal on someone else's computer, you can use the thing via cryptography to take a tunnel into that other computer and use it via SSH. So it looks a lot like this. It's just like not running on this computer, it's running on someone else's computer. You can do verification with SSH, or you can do it with the token. Has everyone set that up yet or not? I recommend starting on that now and see if you have problems. Yeah, so anyway, we can create that one. So if we want to get it though, Control C. If I go here, cd ... git clone. So this will get it from GitHub, make a local version here. So if I go, what did I call it? Test repo. Nothing in it. It's just got a license in it. If I go vim, git status, on main branch, nothing. Again, it's initialized the Git repo that I've pulled from the internet. Same thing. If I change this text file, don't change the license. Okay, git status. It'll go, it's changed. So git add license, ls, git status. It's modified, so I need to commit it. Git commit. Control X. Okay, so I've committed this thing. Git K. If I look at this repo, I've modified the license. You can see that I've added this stupid little bit of text at the end of this license. You'll notice that this is only on my computer. I'm racing to get to this bit. Sorry, it's gone a bit over time. This is only at my computer at this time. If I want it to go to the remote, I have to push it. So this, when I've cloned this repo, this guy here, this license has no changes. This is just on my computer. It's required for you, once you've made a change on your local one, you go git push. And it goes up to main. We can see if I refresh this here, magic of the internet. There we go. There's my little change there. So push to the remote one, pull to get it from the remote one to your one. It's the last one. So if I edit on here, you can do this. Okay. Commit changes. Update license. This is basically doing all that git command line stuff. You'll notice my one here does not have this. That change isn't there yet. If I git pull. Cool. License is updated. And you can see the last bit's gotten there. Basic driving git, got to keep in sync with the remote. That's the thing where you'll have problems. So every time there's been a change, keep pulling often and make sure you keep up to date. Really, I'm going to go through this again. Just wanted to run you by some basic git commands. Please practice. If you break something, call a tutor or me. Just sort it out early, I think. Cool. Thanks, everyone. Yeah, sorry about that. No, it's all fine. I'll just stop this.